Word. He's taunting me. Yeah, the Twitch views are up, man. Way up. Okay, so now that we've all commiserated, I'm not gonna let you tell you my Steam name. Maybe after the semester, but probably still not. All right, so let's begin. So, does anyone have any questions before we begin this new and daunting subject of antiderivatives? It's just how I was made, I suppose. Anti is not on the module. Just regular derivatives. So the module will cover differentiation techniques, stuff like product rule, power rule, quotient rule, chain rule, and you'll need to know about what does the derivative represent. So if I say that f prime of 2 is 5, what does that really mean? It means that the slope of the tangent line to the curve at x equals 2 has slope 5, or the tangent line to the curve at x equals 2 has slope 5. So stuff like that. All right. It was not me. We will, yeah. So it'll start Friday afternoon, and we'll review for it on Friday as well. Okay. So I'll talk more about it then for sure, and kind of show you, at least for the written part. I mean, the online part, the MyMathLab part, you just kind of do it. The written part, I'll talk more about what kind of answers we're looking for. Okay, so now let's begin today's lesson. So we'll look at antiderivatives. It won't be like so many pages. You'll still be solving a math problem. We'll just want you to explain more what you're doing. So it won't just be rote computations. You would need to explain a little bit about what you're doing, maybe in a few sentences as you do it, or at the end, say oh, I used the chain rule. This was my outside function. This was my inside function. Some kind of stuff like that. Okay, so this is the worksheet. This is posted under my tab on Blackboard as well. So antiderivatives. So the idea, so I'll give a one sentence sort of description about antiderivatives here. So generally the process has been what we've done so far has been given, the question we've been asking is basically given f of x, what is the derivative? Okay, but the question we're going to try to answer today and going onward is sort of the inverse. So if I know the derivative, can I recover the function? What is going on? Yeah, exactly. We're doing the inverse problem. So if I'm given a function that I know is the derivative, can I work backwards and say what f is? It's generally a much harder problem, actually. All right, so we'll get started on that today. So to begin with, we'll look at, so actually we'll just do some stuff that we've already done to start off. So we'll look at the derivative of the natural log. So what is the derivative of ln of x? Just 1 over x, right? Okay, the reason this sort of stipulation is here is because the natural log function is only defined, at least ln of x, like the base ln of x, is only defined if x is greater than 0. Right? I can also define the following function, the natural log of negative x, if I let x be a negative value, because then the two negatives cancel out, and I'm okay. All right, so why don't y'all take a second and try to evaluate this derivative. So note you'll need to use the chain rule, right? Because the inside function isn't just x, now it's negative x. Oh. Whoa, whoa, whoa. Let's be civil, please. Yeah, you tell him, Milos. Order in the chat. Okay, so I had to reconnect my clone. He surreptitiously disconnected, so I couldn't see your comments before. But yeah, what did we get for d over dx, ln of negative x? Good, 1 over x, right? You use the chain rule, so the derivative of the natural log of 1 over x means you take the reciprocal, and then you multiply by the derivative of negative x, which is negative 1. That's right. All right, so note that the absolute value function can be written as a piecewise function, okay? Where the absolute value of x is just regular x if x is positive, and it's negative x if x is negative. So that allows us to basically make the following claim, that the derivative of the natural log of the absolute value of x is equal to 1 over x. So this is true. Okay, so in the language of antiderivatives, we could say that the natural log of the absolute value is an antiderivative of 1 over x, because the derivative of the natural log of the absolute value x is 1 over x. So that's what an antiderivative basically means. Like you say one function is the antiderivative of another if when you take the derivative, you get that other function back. So it's just sort of the opposite relationship. Okay, note that so the antiderivative, one like example of an antiderivative of 1 over x is the natural log of the absolute value of x. Okay, there's actually a whole family of functions that satisfy this. So, for example, note that the derivative of ln So say I took the natural log of the absolute value and I just added 2 outside of the function, and I took the derivative here. What would I get? Good, just 1 over x, right? Because the derivative of 2 is just 0. So this is also an antiderivative, right? And in general, I could add any constant, and it would still be an antiderivative, right? So antiderivatives sort of give you a family of functions. Yeah, it's not too bad, really. You just have to remember to like add a constant at the end, okay? So we'll look at some sort of consequences of the being 0 or 2 functions having the same derivative. Like if 2 functions have the same derivative, what does that mean? Does that mean that they're the same function or what? So we'll look at that here. So for example, from the mean value theorem, if f prime of x is 0 on an interval, then f of x is constant on that whole interval. Okay, the reason being is that what does the mean value theorem say? It says that there's some value c in this interval where f prime of c, let's see if I might have to zoom in to write this out. Okay, but if f prime is always 0, then this would imply that f of b minus f of a is 0. So f of b equals f of a. And I could pick any points kind of like in the interval and apply the mean value theorem over that like subinterval and get the same consequence. So if the derivative is 0, then your function is constant, right? If your derivative is like 0 on an interval, then your function is constant on that interval. Yes, thanks, Howard. Yeah. I'm going to blame that on my pen. Okay, for this next question, true or false, if f prime equals g prime for all x in an interval, then is it true that f of x equals g of x? Once, all right, so let's pull the peanut gallery, see what you think. If f prime equals g prime for all x in an interval, then f equals g on that interval. Basically, if the derivatives are the same, does that imply that the functions are the same? So that's the idea behind the question. So the answer is that it's false. Okay, so 2 functions could have the same derivative but not be the same function. So for example, we'll sort of write it out analytically, and I'll give like a little example. So I could have 2 lines that are parallel. So, so for example, if I have these two functions, the two graphs of these functions, 2x and 2x minus 1, um, what is the derivative of either of these functions? 2, right? So they have the same derivative, right? If I think of this as like f and g, they both have the derivative 2 constantly, okay? But they're not the same function, all right? So the relationship between them is that one is just that they differ by a constant at all points. Okay, so they're not the same function, but they differ by a constant. Okay, so we can see that here. So if f prime equals g prime, um, we can kind of like prove that like two functions that have the same derivative only differ by a constant. So let's make a new function h. And h will be the difference between f and g. Okay, so I could take the derivative of h, so which will just be f prime minus g prime. And what is f prime minus g prime? 0, right? Because f prime equals g prime. So if they're the same thing and I subtract one from the other, I get 0. All right. So h prime is a function whose derivative is always 0. What could I say then about h? What is a function whose derivative is always 0? Good. It's a constant. So h is a constant. Okay, I may not know what that constant is. It could be h of x equals 2, or h of x equals 5, or h of x equals pi, or something like that. But it doesn't really matter. The point is that it's a constant. So if h is a constant, then so is f minus g. So that means that f of x minus g of x is some constant c. Which means that f of x equals g of x plus c. So two functions that have the same derivative they're like almost the same function, or they're the same up to a constant. Okay, so now let's look at finding antiderivatives. All right. So say I have a function f such that, or say I know that f prime, so the derivative of some function, equals 1 over x plus x. We want to find every function f that makes this true. Okay. So remember in the case we did before, we saw that ln of the absolute value of x is an antiderivative of 1 over x, but so is ln of the absolute value of x plus 2. And I could add any constant to that. And if I still take the derivative, I get 1 over x. All right? So really, there's a whole family of functions whose derivative would be 1 over x. All right? So I'm going to break y'all into groups and let y'all try to figure this one out. So think about, so like the 1 over x part we've kind of done already. But you need to think about like what function has the derivative x. Okay? So I'll break y'all out into groups. Okay, so I'll be back in the main room now. So this is basically asking you to find the antiderivative, or the antiderivative or family of antiderivatives of this function 1 over x plus x. Okay, and you do it sort of linearly, just like you can do with derivatives. Like the derivative of f plus g is just f prime plus g prime. Okay, so you can take this like one term at a time. Okay, so what was an antiderivative for 1 over x? Good. ln, it was ln with the absolute values around the x. Okay. Now, what is a function whose derivative would give me x? Okay, good. So y'all are on the right track with like x squared, and indeed like x squared over 2 is the correct answer. Okay, think about x squared. If I take the derivative of x squared, I get 2x, right? But if I take the derivative of x squared over 2, then I just get x back. Okay, so you need to account for that constant, basically, right? So x squared over 2, and then we add c, where c is just represents some constant. Okay, because I could add 5 or 10 or 100 or negative a million at the end. And when I take the derivative, the constant term just goes away, right? So it's still valid, or so it's still correct, right? So let's look more generally at there's sort of basically a power rule for antiderivatives. So you'll basically learn a bunch of these like rules that we've talked about again. So yeah, the C represents, yeah, you need the constant to be completely correct. Because it's saying this says find every function f. Well, if you don't put the c, then you're just giving one function, but it's not the only correct answer. So ln of x plus x squared over 2 is like one correct antiderivative. But so is ln of x plus x squared over 2 plus 5, or ln of x plus x squared over 2 plus 10. Those are also correct. So we use the c to represent like all of those. Okay, so the antiderivative of x is x squared over 2, and it gets kind of pedantic, but I'll keep putting the plus c here. What is a derivative, or sorry, an antiderivative of x squared? Good, x cubed over 3, exactly. You need the over 3 to sort of account for the fact that when you use the power rule, you bring that 3 out front, and you don't want that coefficient there. Okay, and in general, x to the n the antiderivative will be x to the n plus 1 divided by n plus 1 plus c. So look at what happens when you take the derivative of the right-hand term. So you can, like, one nice thing with these antiderivatives is you can generally check your answer. Whatever I get, if I then take the derivative, I should get the original function back. So if I take the derivative of x to the n plus 1 divided by n plus 1 plus c, the power rule tells, yeah, this is in here is an arbitrary. It could be, yeah, anything. Any number. All right. So when I take the derivative of this term here, now you're taking the derivative using the power rule, right? So that tells me to bring the n plus 1 down. And reduce the exponent by 1. So n plus 1 minus 1 is just n. The derivative of c is just 0. And these n plus 1 terms cancel out, and I'm just left with x to the n. Okay, so let's talk through these next couple as well. All right, so if I have f prime is 1 plus e to the 2x, then let's see what f could be. Okay, so again, you basically take these one term at a time, and then you just add c. All right, so what is a function such that when I take its derivative, I would get 1? Good, just x. just 1x. Okay, and how about for e to the 2x? So e to the 2x is a good base point. And then, yeah, right, you'll divide by 2 to deal with the fact that when you would take the derivative, you would pick up a 2. Okay, and then we add c at the end. Yep, that's it. So really, thinking of e to the 2x is the important thing. And then you can kind of, then I divide by 2, but you can kind of adjust for that, as you get to it. All right, but knowing that like the derivative of e to the 2x looks like e to the 2x. So I'll use that because if you take the derivative of e to the 2x, you get 2e to the 2x. But I don't have a 2 out front there, so I need to divide by it. So again, you can always check your answer. Like if I had only put if I had only put e to the 2x without the dividing by 2, I could think, well, when I take the derivative, I pick up a 2. Like I pick this 2 up out front. So how do I avoid that? I can avoid that by dividing by 2. So then I divide by 2 here, and those cancel out. Okay, so let's look at the next one, and we'll look at this like how we can kind of like adjust the constants as we go. 3 sine x is the next term. So what function would give me what function has the derivative sine? Okay, so cosine is the right idea. What's the actual derivative of cosine? Right. So Jared, you're right, and right. The derivative of cosine is negative sine. Okay. So if my function here is a positive sign, I adjust that by like putting a negative in front of the cosine. So negative 3 cosine x will be what I have here. That's the function whose derivative gives me 3 sine x. Yeah, the c, Jamie, the c just represents a constant, because if I add a constant to any function, the derivative of constant is 0. Okay, now let's look at the next function. So sort of ignore the 2 for now. Like think about the 2 as being out front, right? What function has the derivative 1 over 1 plus x squared? So this one maybe is a little trickier. So it's not quite tangent, but it's almost, it's like the opposite of tangent. It's not a trig function. Arctan, that's it. Yep. Inverse tangent, exactly. So the derivative of arctan was 1 over 1 plus x squared. All right. So the antiderivative of 2 over 1, like 2 is just a constant. That's just being multiplied through it. So when you do the antiderivative, you'll have 2 times arctan of x. All right, then we have 1 over root x. So what function, like again, we can adjust for the constant, what function like sort of has the derivative like 1 over root x? No, we're using arctan because the derivative of arctan is 1 over 1 plus x squared. Yeah. Okay, so square root is the right like idea, right? The derivative of the square root function is 1 over 2 square root x. Right? So the derivative of square root x is 1 over 2 square root x. Okay, so what constant should I multiply square root x by so that I get rid of this 2 on the bottom? Right, a 2 or like negative 2 if you're thinking about the negative out front. So I can put 2 square root x here. Okay, and then what function has derivative 3? Good, 3x. So constants are pretty easy to deal with. Like the antiderivative of a constant, you basically just tag the x on at the end. Okay, and then we have to remember to put plus c. That's a bad line. Also bad. One more time. Beautiful. Don't forget the C. Truer words were never spoken. Thank you, thank you. Please clap. All right. Okay, so actually, let's now look at a problem where we can get rid of the C. So the C basically represents an initial value, which we don't know. The idea is that if I take an antiderivative, I could get, maybe I get 2x, or maybe I get 2x minus 1, or I get 2x minus 5, or 2x plus 5. Those are all functions that have the same derivative, okay? And they all differ by a constant. But there's a way to specify like what that constant should be, and we'll do that here. So assume that capital F is a function whose derivative is 2x plus 10, and I know a specific value for f. So I know that f of 0 is 2. All right, so this is called an initial value problem because it's saying, like, what is the value at 0? And it's 2. And we can use this to kind of get rid of the c. All right, so I know the derivative of f, and I know its value at a given point. So now I can do this to sort of unambiguously write down f without this plus c at the end. All right, so first we'll deal with the c. So f is the function whose derivative is 2x plus 10. All right, so we're looking at an antiderivative here. So what is an antiderivative of 2x? Good, x squared, right? And exactly x squared, because when you take the derivative of that, you get the 2 out front. All right, what is an antiderivative of 10? Good, 10x. Okay, and for now we will have this like plus c out here, but we'll see how to like solve for c. All right, so we'll basically just use this data here to solve for c. The fact that f of 0 has to be 2. So f of 0 is 0 squared plus 10 times 0 plus c, which is just c, but I also know that it has to equal 2. Okay, so now we've solved for c, basically. We found out that c is 2, and the actual function f is x squared plus 10x plus 2. Okay, so now you've solved your first initial value problem. A pivotal moment in anyone's life. Congrats. So if it said that f of 0 is 3, then you would do it. If they tell you that f of 3 is something, then you would plug through. Like I plugged in 0 because I knew the value of f at 0. If I knew the value of f at 3, then I would plug 3 in and work it from there. And it would be harder to work out, basically. Okay. All right, so last problem. So a ball is thrown directly upward at a speed of 64 feet per second from a platform 80 feet above the ground. Assume that the acceleration is negative 32 feet per second. All right, so this is sort of the reason behind like the existence of calculus, basically. Solving kinematic problems was the impetus for it. And if you didn't know, Isaac Newton actually invented calculus while he was in quarantine from the plague. So I hope you're all using your time wisely and productively. I know I am. All right, so let's try to solve this problem in honor of Isaac Newton's quarantine. Okay, so a ball is thrown upward at a speed of 64 feet per second. from a platform 80 feet above the ground, and we know that the acceleration is negative 32 feet per second. Yeah, he actually invented gravity too. It's true. Everything floated before. All right, so we've talked about this before. Basically, we have like position and velocity is the derivative of position, and acceleration is the derivative of velocity. Okay, so if we know that acceleration is negative 32, what is velocity? So this is just asking basically what is the antiderivative of the acceleration function. Good, negative 32. And then actually, yeah, Sophie's right. We want to use the variable t because like everything we're writing down is a function of time. Okay, so it's negative 32t plus c. Okay, how do we find c now? All right, so this is still an initial value problem. So I can find c if I know a specific value of the velocity. So can anyone tell me based off this problem, the statement of the problem, what is the velocity at time 0? Good, 64, right? It says someone threw a ball upward at a speed of 64 feet per second. Okay? So we find that c is 64, and the actual velocity function then is negative 32t plus 64. All right, when does the ball reach its highest point? So if I throw a ball up and it comes back down, how would you characterize the velocity when it reaches its highest point? So the velocity would be 0, right? So you set velocity equal to 0. Okay, and you end up with t equals 2. So after 2 seconds, the ball will reach its highest point. All right, when will the ball hit the ground? So remember, I'm sort of standing 80 feet above the ground. I throw the ball and eventually it hits the ground. All right, so I'm going to do something similar. Yeah, exactly. So I'll set the position equal to 0. All right. But I don't have a position function yet. All I have is a velocity function. Okay, but we know that velocity is the derivative of position. Okay, so position is an antiderivative of velocity. So if I know that v of t equals negative 32t plus 64, I can solve, or I can take its an antiderivative and find the position function. Okay, so what is the antiderivative of t? So sort of ignore the negative 32 for now. So it'll be negative 32 t squared over 2. All right, and then write the antiderivative of 64 will give you 64t, and then we'll still have this plus c. Okay, and c is just the initial value for the position. So if I plug 0 in, I'll get c, and then what is that based off the statement of the problem? Good. 80, exactly, right? It says I'm standing on a platform 80 feet above. Okay, so S of t has the equation negative 16 t squared plus 64t plus 80. So we solve for the position function. Yep, and then you set it equal to 0. So you can factor out, so I'll do that real quick, how you would solve that. So at that point, you're just factoring, basically. You can factor out a negative 16, and you'd get t squared minus 4t minus 5 equals 0. This factors as t minus 5 times t plus 1. So you get that t is 5 or t is negative 1. And only one of these answers makes sense. So when does the ball hit the ground? Good, at time 5, exactly. Right, we don't really include the negative time answer. That's before I even threw the ball. Okay, good. So you get t equals 5. All right, so that's been our sort of introduction to antiderivatives. We'll have a lot more to say about this as the course goes on. But for now, that'll be all. Sorry for going a little over. I will have office hours in the main room. And we'll talk about the module on Friday. All right, glad to hear it. Yeah, this is a meme friendly zone. Thanks, y'all too. All right, I'll see y'all on Friday. So you go to the main like online classroom. If you go back to the online classroom tab uh, from Blackboard, and then like the very first room will be where the office hours will be. I think it just says like Math 180 basically. Yeah, the course room. Preach. There's no D in my name though. All right, so I'm going to go over to the main room. I'm going to leave this and go over to the main room in a bit to have my office hours. All right, so I'll see y'all later if you don't show up.